The last topic I want to talk about is Rust. Rust is getting a lot of attention. It's a very new language. It's still in development, so I've read people that argue it's not really ready for prime time yet. But the great thing about Rust is it solves the enormous security problems, the memory corruption problems caused by C. And there's a lot of talk about writing at least part of Windows in Rust to try to get these vulnerabilities out of it. And so I was very pleased to demonstrate these vulnerabilities and how to fix them. So I'm just running Rust on a Linux machine. And by the way, one other thing that bothered me about Rust is the files seemed very big, but I read in a blog after I wrote these projects that by default the Rust compiler adds debugging information, and you can turn that off and then the files are not bigger than Linux. So that might be true. Anyway, so there's just a few commands to install Rust on Linux, on Debian 10, so I already did that. And then you can have a Hello World app, which I just set up here. So this is what it looks like. It's a lot like C, right? I don't know what the FN is for, but you have a main function where it starts, and then in here you have print line. The exclamation point is a little funny, but anyway, that's going to print a message saying Rust says hello. And so it does. When you run that, it just prints that message. So that's a start, showing that I've got it working. And now we can play with integer data types. So I'm using Rust the same way that Go is these days, where you make a separate directory for each app. And that's recommended for most modern languages so you can keep all your dependencies under control. So anyway, in here I'm going to define a few variables and print them out. So you use let to define a variable, and you can have I equals 1. And you can have j colon I32. Now there is a tutorial here to tell you, and I guess I'll probably just give away a flag here. If you read this, it tells you the way Rust works. You define various types of variables. There's signed and unsigned in 8, 16, 32, and other sizes. But there's this weird thing with the colon. And if you don't tell it what to do, it will assume I32. Okay, so let's run this and see what error I get. Let me go back to my instructions. All right, so if I compile it, it should tell us what's wrong here. All right, and I cannot apply minus to an unsigned interval, right? We just said so signed and unsigned. This is unsigned. An unsigned interval variable cannot have a negative number. Now notice that is already something that is not true of C. C will just let you put a negative number in an unsigned integer, and it will just be the wrong value. Rust won't let you do that. All right. So anyway, that's easy enough to fix. So there's one where you're adding a couple numbers, and you have to figure out what's wrong with them. And then let's go on to the really fun stuff, which is integer overflow. This is where we start creating programs that make trouble in C. So here's an integer overflow in C. All right, so I define an unsigned character. This is what's so horrible about C. This is what took me a long time to get over. I was accustomed to interpreting 1 byte as equal to 1 character because that's the way it is in C. Now this is a really stupid idea because it only works if you only think English exists. If you consider the other languages, you need more than 1 byte to indicate 1 character, and that's Unicode. But Rust or C is still thinking this way. So I define a character of X, and then I put in the number 230. Okay, then I'm going to add to X, add and add and add, and make it bigger and bigger, and see what happens. So if I run that, I compile it and run it. I take this number, I add to it, add to it, add to it, and when I add to it again, it rolls around like an odometer and gets small again. Now this is crazy. This leads to no end of problems for developers, for security, and everything else. Why would you make a language this stupid, where I have a number, I add to it, and then it gets small? How am I supposed to remember that and never make that mistake? This is just cruel, but that's what C does to you. Rust does not do that to you. If you try to do the same thing in Rust, it won't happen. So here's the same program in Rust. I define a mutable variable that is an unsigned 8-bit number 230, and then I try adding to it in a loop. And so if I compile that and run it, Rust will add to it until it gets above 255, and then it will stop and say, you tried to put a number that was too big in there, I stopped. So this is, of course, much better. It tells you there's a problem and you have to fix it. It doesn't just blithely put the wrong value in there and keep going just to ruin your program. So it's much better. All right. And the same thing with the other vulnerabilities you'll see in C. Here's a string overflow. All right. So I have two strings. One has 4 A's in it, one has 4 B's in it. I'll write down where they are and what's in there. Then I can enter a new value for this one. And when I use scanf, it does not restrict how many characters I put in. And then I look to see what happened. So when I run this, okay, it tells me I have AAA in the first string and BBBB in the second string. The first string is here at address 2B. The second string is here at address 26. So if I were to put in a value for string 2 that's longer, it will leak over into string 1. So now I changed string 2 to these G's, and that worked, but string 1 changed to these G's when I had no intention of changing it at all. And again, I have great sympathy for the developer. How was I supposed to know that would happen? I change one string, some other string changes. It doesn't give me an error message. It doesn't crash. Why would anybody use this horrible language? And again, Rust solves that problem. So here's the same thing in Rust. You have two strings. You print out the addresses and the values. Then you enter a new value. And then you print out the strings again. Does just the same thing again. And if you run that thing, all right, I run it. It asks me for a new value for string 1. Now notice the first string is at 340 and the other string is at 358. So I already, now I'm going to have to, string 1 is the one that's in first. So I'll put in a new value for string 1. And if I make it long enough, it should leak over into string 358 there. So let's make it really long. I have to have 16 plus 8 more to hit it. So that's got to be enough. And now what happens is string 1 added those to the end of it instead of changing it. And string 2 is unchanged. But string 1 is still where it was. String 2 is still where it was too. That's because if you look at what's actually there in a debugger, what's actually there is not the contents of the string. What's actually there is a pointer to the string, which is somewhere else. And it has changed that pointer to point to an area with enough room to hold the bigger string. So it's not as simple how it stores strings, but it is more effective in that it will not take the data you put in one variable and just put it in some other variable, which is madness. And you can use the debugger to see how it stores the strings and find out how that works. All right. And then there's command injection. So if I do this one, this one here is going to have two variables. One is a command and one's an IP address. And then the command is going to be ping minus C1, and it's going to read the IP from me. And so again, if I can put in an IP address that's long enough, I can overwrite the command. And when it tries to execute the command, it'll be executing a command that came from me. That's how command injection vulnerabilities work. So compile that and run it. And now if I give it a normal IP, it pings that IP, which was the goal. It was going to do ping minus C1 and then add the IP by adding those together. But if I put in a semicolon, that was it. It was nothing to link, it's the semicolon. So I put in 8.8.8 semicolon date. It will do the ping and then print out the date. So I can add an extra command at the end with the semicolon. So I can do this in Rust. and this line at the bottom. This, I think, is how you get command line execution in Rust for the command library. And now I make my Rust source code. And I use the command library run command so I can now run a command. All right, and so again, it'll enter IP it gets from the user, and then to a ping of that IP. Okay. And unexpected closing delimiter. Oh, I failed at my source code somehow. I did, didn't I? I left an extra closing delimiter in there. Okay. Okay, now I can give it 8.8.8.8, and it pings it. And now I can give it 8.8.8.8 semicolon date. And it still has the vulnerability. So this is one that Rust cannot fix. If you compose a command and you put an unexpected character in that command and it runs it, it has no way to know you didn't mean that. It's not a fundamental flaw of the programming language. That's a real logic flaw that came from the user. Anyway, so there's some Rust stuff, and I've got another bunch of them here where you can do dangling pointers and memory leaks, which are more vulnerabilities. And again, here's a heap overflow in C and a heap overflow in Rust. There is no overflow. Just like the other overflow, when you try to make one string so long that it hits the next string, Rust will not fall for that. It will reserve another room big enough for the big string, just like Visual Basic or many other languages. It will not let a string get longer and outrun its bounds. And you can examine how it's stored in the debugger to see that. And I was able to make a dangling pointer here, where you define a pointer to something, and you allocate space, and then you free it, and then you allocate more space, and then you can still use the old name even though it's been freed. That's the thing. And so anyway, that I think also Rust fixes. It won't allow the developer to make the mistake of using a name after it's no longer allocated. It will fail at compile time, saying you can't keep using this variable after it's been freed, which is one form of dangling pointers. So anyway, and then there's a memory leak in C where you allocate space but you never free it, so it just uses up more and more and more space. And I think in that one, yeah, the memory usage is constant. Rust has no memory leak. It automatically frees memory each time it returns. You don't need to manually free it, so you can't make the mistake of forgetting to free it. So, you know, it's pretty impressive. All right, and I was able to make a memory leak in Rust by trying hard enough, but it wasn't that easy. Anyway, that's an introduction to the joy of Rust.